Thanks, Stephen. And I like he introduced me as I promote the use of data science in public policy because that's pretty much what I do. I don't actually do anything real. So the real work is done by other people. I just come and promote the work. So a lot of people in the audience have been involved in those efforts that I'm going to talk about. So what I sort of like to do is start talking about some really depressing stories. Because it's after lunch, we're all kind of tired. So let's kind of bring the energy level down as much as we can and talk about some extremely depressing things. So depressing story number one, police misconduct. We're all very familiar with it. Unfortunately, we're in Chicago. It's not a problem just limited to Chicago. The relationship between police and the community is probably at one of the lower levels it's ever been. And it's not getting any better. And although the use of data science isn't really is going to fix the core problem, but one way to sort of think about what this problem, how police departments have tried to tackle this problem for many years is they've had these systems in place what are called early intervention systems. And these systems are designed to raise early warning flags when an officer is likely to have what's called an adverse incident with the public. That could mean excessive use of force, unjustified use of force, a complaint, any type of injury. And so the way these systems work today is they basically don't work. Because they're designed by people sitting on a table thinking about what could be predictive of an officer, of an adverse incident. So, well, perhaps it's the number of times a complaint against him has been filed, or perhaps it's the number of uses of force in the past. So here's an example of a system that Charlotte Mecklenburg in North Carolina had built. And this is pretty much the state of the art right now in the US. And the system basically comes up with, not system comes up, but you go into the system. It's clearly .NET, you can see that. It comes up and you sort of put in number of accidents. So it says if 0, and it looks like this one, right? So if 2 complaints have been filed, or 3 complaints have been filed against a person in a 180-day period, raise a flag. It says if they've had 2 uses of force in a 90-day period, raise a flag. As you can imagine, the problem, there are many problems with the system, despite other than the .NET problem. But the problem with these things. I haven't even started talking and they're already not saying much yet. Okay, so the problem is, one of the problems with the system is that these are not early warning flags, right? These things have already happened and now telling the police department something bad is happening. So one, it's just the interventions at this point are mostly punitive. All you can do is fire the person and there's not much else you can do. The second thing is when you start looking at the data behind it, that these types of flags raise, they basically flag a ton of officers. So in the case of Charlotte, it turns out that a system like this flagged about 60% of the officers in the department. And it still failed to capture about 20-25% of the officers who ended up doing bad things in the future, right? So it's not only inaccurate, it also is unreliable because it keeps raising flags about everyone. So the goal for a system like this is it has to be accurate, it has to identify as many people correctly as possible, but you also have to minimize the number of false positives. And so what we started doing was, one, started looking at the system, at the data behind these systems, and started getting data from departments, and building a system that could do better. And in this case, we worked with a few different departments. So we started working with Charlotte about a year and about a year and a half ago, and we've kind of added a few other departments to this pool, and we got data about everything they know pretty much about an officer. So their employment history, their demographic data, their training, their any arrests, any dispatches, any citations, any stops, any complaints against them, whether the complaints were justified, unjustified, were they investigated, what happened throughout the entire process. So you're basically seeing pretty much everything. There are sort of some exceptions. And based on all of that, we want to predict if this officer is likely to have one of these adverse incidents in the next period, whatever the period is, whether it's 3 months, 6 months, 12 months, 18 months. And the period really depends on how much time you need for that intervention to work. If the intervention is take him off the street and put him on the bench, that's one type of intervention. If it's a counseling intervention, if it's a training intervention. And what we were able to do pretty quickly was find out that using off-the-shelf machine learning sort of methods, if you sort of structure your inputs properly, if you start sort of setting this up, you could pretty easily do better than the system that existed, right? So what we're able to do is show that you can actually reduce the number of false positives by about 50%, while increasing the number of people you're actually finding correctly by about 15 to 20%. Now, what that allows people to do is it actually makes it an early intervention system, as opposed to something that's one, not accurate, and two, the interventions can't really be useful. You can start doing it early. And one of the extensions to that, which one of the teams this summer of this fellowship program that Steve was talking about was working on is, how do I now support other types of interventions? For example, when you're doing a dispatch, what a police dispatcher does today is a call comes in, and they look at sort of what type of call it is, they look at sort of where officers are in the area, and they try to kind of dispatch the nearest officer to that call. Now, what if we could predict that this officer is at high risk of an adverse interaction for this dispatch? What if that officer was 2 minutes away and the next officer was 3 minutes away, but at a much lower risk? Is the urgency of that call low enough that you could sort of make that trade-off? Could you be smarter about who to send, not just based on the distance and the type of dispatch, but also their risk? So we're finding pretty good results. Now, dispatches are very, they happen all the time, and a very small percentage of those dispatches end up being adverse incidents. So you want to be very careful about how accurately can you predict those things, and then how do you prioritize those things. So that's sort of depressing story number one that's happening today. And I'll sort of try to go through a bunch of examples as opposed to going too deep, but feel free to ask me questions, as well as I can point you to more detailed write-ups of these things, including the GitHub repos for all these things are public, so you can take a look at those things as well. So depressing story number two, this one actually takes place in Chicago. It's lead poisoning. And a lot of you are probably more familiar with lead poisoning now than you were 6, 9 months ago, mostly because of Flint. But it turns out that lead poisoning, the major source of lead poisoning is not lead, water, and pipes. It's really lead in paint. So every home built before, the US before 1978 has lead paint in there, and that paint is fine as long as that stays inside that wall. But as homes get old, lead starts coming, paint starts chipping. Kids, when they turn, 12 months, 11, 12 months, they start crawling. And when they start crawling, they pick up lead dust with their hands, they put it in their mouth, it goes into your bloodstream, and it has pretty horrible effects. Lower IQ, hearing loss, memory loss, motor control issues, all very bad things. The worst of all those effects are irreversible. Once there is lead in your bloodstream, there's not much you can do to reverse the damage. So the way we deal with that problem today is we wait until somebody is lead poisoned. So for example, city of Chicago, every kid is supposed to get tested, their blood's supposed to get tested for lead levels. And when they get tested, if there is an elevated lead level, the health department gets notified. The health department then sends a team to the home where the kid lives to check for lead hazards. And sure enough, 98% of the time, they find lead hazards there because the kid got poisoned. So they go in, check for lead, they find it, and they figure out how to remediate those problems, which means like repainting the wall or replacing doors or windows if it's in there. Now, the problem there is obvious, right? Where the damage has already happened. By fixing this home, we're protecting future kids who might live in that home from lead poisoning. But the kid who just got poisoned, well, too bad. So our policy, effective policy today, is we use kids as lead sensors to detect lead, and then go and fix the problems because they're extremely accurate sensors. It sounds horrible, but that's our policy for all practical purposes. Now, to their credit, they realized that was a bad policy, but they didn't know what to do about it. So they came to us and said, well, is there a way we can find out before they get poisoned and do something about it before? So we started working with them on getting data for the nice thing is a lot of these problems, the data already exists. It's being stored for a compliance and regulatory purposes, and now we can sort of repurpose it to do more useful things, right? So data that existed in this case was every blood test in Chicago was stored. So now we know which kid, where they live, and what was their blood lead level. The second thing we had was access data to every lead inspection that was done. So we know this home was inspected on this date, and whether lead was found or not, and then some information about remediation in the future. You could now augment all of that with some open data about home structures. In this case, you've got pricing for the house, what structure it was, what the material, when was it built, how many rooms are there, how many floors, all of that stuff. Using all of the data, what we could do is basically structure this problem so that what we're doing is taking a kid, just like in the police officer case, at a particular age, and that age could be anywhere from -6 months. So if somebody is pregnant, we can start from there and say, hey, if the kid were to be born in this address, how likely is this that this kid is going to get lead poisoning? Or it could be as late as 12 months, because you don't want to predict after that because it's too late. Right? So we take every kid between that age, and now we can predict what's the risk that this kid is going to get lead poisoning. And if we can predict that, then we can direct our inspectors to go there before the kid gets poisoned and start fixing the process. And the reason you want to ideally do it before birth is so that you have more time, because once the kid is born, one, you have to do it pretty quickly, but two, there is some reason to believe that when you go in and you basically drill into the wall. When you drill into the wall to check for lead, dust comes out. So it is a slightly elevated chance. It's still better than not doing that. So that we were able to show that we can fairly accurately, compared to what they were doing before, which was nothing, right? It's all reactive, so we're not saving any kids. Compared to that, we could do these preventative inspections so that you could start remediating these homes before the kid gets poisoned. And so what the city is doing right now is we're doing two different things. One is they've started a pilot, basically an experiment, that's comparing if they were to do their process as they were doing, and if they were used this predictive model, how much better would we do? The second thing we're doing is working with a couple of hospital systems to implement this into the electronic medical record system. So when a pregnant woman comes in for a checkup, it raises a flag saying, hey, this kid who's going to be born is likely to have lead poisoning. That's going to go back to the health department, just like the post-poisoning report was going. And so then now they have time to go and prioritize and allocate the right resources. So story number 3, high schools. About 30-something. I'm going to try to see if I can turn this thing off. Or reply, maybe. Okay, so story number 3. About 30% of high school students drop out or not graduate on time in the US. And that number is pretty similar to most of the developing countries in the world. So pretty bad shape. And at the same time, you sort of hear about there's a lot of money being spent on support programs, after school programs. So there's a lot of funding there to create these programs, and it's not affecting the dropout rate very much. And so one hypothesis a lot of people have is that we've got these programs, but these programs are not really targeted at the right kids. Often these programs are opt-in, so you have to go sign up, or a parent has to go sign up for these programs. And that somehow typically defeats the purpose of having these programs, because a lot of kids at risk, they're not going to opt into these things. So one of the challenges a lot of schools face is that they don't really know how to prioritize the kids that are at risk. Because just like, again, the police system, a lot of these systems are built by 3 experts sitting around a table thinking, oh, okay, so if the GPA of a student is less than 2.9, that's probably at risk. And if they've missed more than 3 days of school, they're probably at risk. If they've had 4 disciplinary actions against them, then they're probably at risk. Now what that does is, again, it flags a ton of kids, and so you miss a bunch of kids who are at risk. So you miss a bunch of kids who are not in this set, but also when you intervene on 60% and 40%, 20% of kids, a lot of those interventions are wasted, because you could have taken those interventions and applied them to kids who richly needed them. So again, you're being inefficient, and you're missing a bunch of kids. So there's this mismatch. So we started looking at with several different schools around the country. So we worked with Montgomery County in Maryland, Cabarrus County in North Carolina, Mesa in Arizona, and then about 15 school districts this summer in southeastern Ohio to try to build a system that's able to accurately identify the kids who are at risk. And it's very similar to the previous two things, right? You take everything you know about a kid, and instead of 3 experts sitting around a table and trying to come up with these things, you use data. And you take everything you know about a kid and predict how likely are they to drop out in the next year, 2 years, 3 years, 4 years, 5 years. And so one of the results we found this summer, and so we've kind of shown that it works on a lot of different school districts. The team that was working on it this summer, one of the interesting results they found is that in 9th grade or 10th grade, schools are pretty good at identifying some number of kids who are at risk. What we can do with this additional data and machine learning is we can identify the same kids 3 years earlier. So instead of waiting till the 10th grade to find them, we can identify the same number of kids in 7th grade. So now the school has 3 extra years to figure out, how do I figure out how to keep them in school? How do I make sure they graduate from school? What types of programs actually work? And one of the things to kind of keep in mind is, what I'm talking about here is sort of the identification problem, right? Can I identify and prioritize the kids who are most at risk? And I'm hoping that the interventions that exist are actually able to change that behavior. And so that's sort of the next piece in this type of work. In the lead case, I know that if I can remove the lead from the house, it will not, that kid will not get lead poisoning because I know the physical process of lead poisoning. You ingest lead, it goes into yours. If I take out the lead, you're fine. In the case of dropping out of high school, needing extra support, I don't exactly know what kind of program works for you, because a lot of the studies that are done are they talk about average kids. So on average, this intervention helps kids 3%. Now, what about the kids who are really high risk? Do I know if that works for them? Because I don't know who those kids are, I can't test the interventions. So another sort of side effect, a byproduct of this type of targeting, is you can start designing interventions that are specifically targeted at kids who are high risk, and then you can start validating that so you can test whether your interventions are actually effective or not. So another example of this sort of prioritization and targeting, this is some work that we started doing with the EPA about a year ago, but it's also extended through some other organizations. And here the idea was to, so EPA, for example, is, there's a bunch of different regulations they have to enforce. One of them is around getting rid of hazardous waste. And what they need to do is to figure out, they've got 500,000 facilities around the country that generate hazardous waste. And they have a handful of inspectors who go into these facilities and inspect things. And this is a fairly common problem, right? The organizations have access to a ton of things, and they can only investigate a few of them, and their goal is to enforce across all. And so what they end up doing is, again, some experts sitting around a table deciding which facilities should we inspect this year. We can inspect the ones we haven't inspected in a while. We can inspect the ones who violate regularly. We can inspect the large ones. We can inspect the ones that are near where a lot of people live or where there's water sources, so you don't have waste going into rivers. And they end up doing that and end up finding sort of some percentage of facilities that are violations. So what we started working with them was, hey, can we make you more efficient? Can we start targeting facilities that are much more likely to be at risk of violations than you were doing before? And again, the process is very similar. You get historical data about all of their inspections, and you start building models that predict which facility is likely to violate in the future. One tricky thing here is that when you start working with them, their goal is efficiency. They want to make sure every inspection they do is a violation because that's what they live for. But their goal, if you start thinking about this, the goal here isn't finding violations. The goal is enforcement, and the goal is deterrence, right? So if you were doing 1,000 inspections a year and you found 1,000 violations, but in your set of the other 499,000, the violation rate kept going up, that would be failure. So you would be very efficient, but completely useless because you care about minimizing the total violation rate, not the found violations. And that's a very common problem when people do inspections is they try to focus on the efficiency part and forget about sort of the actual deterrence. So the first step was really, if we started telling them to fix that problem, they would never even start. So the first step was really, can we make you more efficient? And once we've made you more efficient, the next step is to kind of move on and start doing the deterrence problem, which we're kind of going to get to in the near future. But a very similar problem also occurs in cities. So this is a home in Cincinnati. And Cincinnati, like many other Midwestern cities, is a shrinking city, right? So people are moving out of the city, and there is a lot of blight. Homes are getting abandoned. That's spreading to different neighborhoods, and it's in pretty bad shape. And so one of the tools they wanted to use, so most cities, when they deal with blight, so take, Midwest, take Memphis, Detroit, a lot of other cities, the way they deal with blight is very similar to the lead poisoning example, is they let it happen, and then they go and try to fix it in a reactive way. So they'll try to get investments into a neighborhood, try to bring it back up, try to get, and that has other side effects that may be good or bad, but it's much more expensive to do it later. It's already affected people's lives, and it's already affected the economy of the city. So what Cincinnati wanted to do is see, can we, again, do it in a proactive way, in a preventative way? And one of the tools they had access to was home inspections. So home inspections are typically, used to, again, enforce code, right? Where somebody says, your roof has to be the structure. They go in and say, that's not right, it's not stable, and you inspect the home, you find a violation, you get them to fix it. What they wanted to do was say, well, can we use these inspections to find code violations that lead to blight? Whether that means that it's going to lead to home abandonment, or whether that means that it's going to lead to home abandonment of that home, which could be a leading indicator to blight spreading through that neighborhood. So instead of just looking at homes that might have violations, they wanted to look at homes that have violations that could lead to blight. And again, the process was pretty much the same, right? Where you get some data, you look at the historical inspections, you try to find homes that are at risk, but now you're trying to figure out the additional thing of, is this violation just a violation? Or is it a leading indicator of something bigger that could get much worse? So you can prevent that from happening in the first place. I'll come back to some of those things in a little while. So one last depressing story, and this depressing story is around prisons and typically jails, right? So there's sort of this, our criminal justice system is in pretty bad shape, right? People keep cycling through it over and over again. And one of the things you sort of actually notice is when you look at people who are in jails for a very long time or for multiple times, it turns out that they also interact with other services that a city, county, or state provides. So homeless shelters, emergency rooms, mental health facilities. And so it turns out that when you start looking at the people, if you look at this is sort of the three systems, right? So this is your emergency room on the left side, the largest one, mental health facilities in the green, and then jails in the blue. So it turns out the people who are going through repeatedly going through the system, they end up being disproportionately kind of here in these intersections in this Venn diagram. And it also turns out that often happens before long stays in jails. So the hypothesis that we have here is, if we could identify the people who are going to get stuck in those systems later, can we provide this information to emergency rooms? Can we provide this to mental health facilities? Can we provide this information to homeless shelters so they could start doing preventative work so that these people can be saved from going into that system in the longer term? So this is some work we very recently started, in this case with Johnson County, Kansas. And some of the results we're finding are actually very encouraging. Because the problem is, you can sort of say, well, 60% of people who spent 1 year or more in jail, they had an interaction, they went to the ER in the 2 years preceding that. Well, that's not very useful because 0.0001% of the people who go to the ER end up in jails, right? So knowing that direction doesn't help you predict other directions. So what we were trying to do is say, what if we reverse? What if we said, you are now in a mental health facility, or you're coming there. Can I predict if you're likely to be at risk of going into jail in the next year? And if I can predict that, can I give this information to a caseworker or a mental health worker, and they can start working with you, and a minimum keeping in touch with you as you leave there to make sure that you have the support you need. And what we found is, this is sort of a graph of, if you start taking the top people that you're really confident about that prediction, how efficient can you be, right? So what we found is that if you take the top 200 people we're predicting who are at risk, 100 of them are going to go on to be in jail in the next year. And if you could intervene with them and prevent that from happening, which is very big if, because we don't know if we can yet, they are going to go on in the next many years to be in jail for 7,000 years. I mean, 7,000 days. Sorry, that would be a horrible. That would actually, increase the lifespan by quite a bit. But it turns out that if on the top 200 we can find 100 people who are actually going to go on and be stuck in jails for the next, for 7,000 days. So that's very early work that we've started doing. I don't have, very concrete results, but it's something that we're extending with a lot of other jurisdictions. So we're working with Salt Lake County, we're working with Milwaukee on very similar problems as part of a larger effort around data-driven justice and criminal justice reform. So I'm going to kind of step back a little bit from these stories. And there are many such stories that are on our website. So go take a look at a lot of these types of projects that we've done over the last several years and that are going on. But one of the things you sort of step back and say, when you start working with cities, nonprofits, states, counties, you sort of end up working with them, trying to teach them, how do you think about these problems? How do you structure these problems so they can solve them using the tools we have access to? And you sort of find certain templates, right? So in this kind of data science for social good templates or public policy templates. And they kind of fall into mostly in these 5 buckets, right? So the first bucket was, can I detect who's going to get lead poisoning early, right? But the template really is, can I detect something early? Like, these are early intervention systems, early warning systems. So whether it's for police officers or whether it's for kids who are going to get lead poisoning, or whether it's for kids who are going to drop out of high school or need extra support in high school, or people who are going to go to jail in the next year, it's an early warning system. The second one is sort of, can I determine which home inspections to prioritize, or which people I want to focus on, or any other thing when I have facilities, and which facilities do I prioritize to inspect? And so that's a prioritization problem where I know I'm not going to be able to get to all of them. I've got this many things, I can only do something about this many. Which ones should they be in order to minimize blight, or to maximize violations, or to maximize deterrence effects? The third one, which I didn't talk about very much, examples, because they're slightly more complicated examples, where a lot of times organizations have access to a bunch of different policies. And so in this case, it was a project we were doing with government of Mexico, where they were trying to reduce maternal mortality. And what they weren't sure about is, we can do a bunch of different things. We can put more clinics around people. We can do better transportation policies. We can do other things. Which ones do I modify? How do I take the 30 policies I have access to, pick the 3 that to prioritize, to test and see which one is more effective? The fourth one is a very common one, which is people do stuff. And when they do things, they don't quite think ahead about, what am I trying to really do? The cities design policies, and they implement them. And then 5 years later, it's like, what impact did that have? Like, well, it would have been nice if you had planned that from the beginning, so you could actually see which policy is effective, so you can then use that policy going forward. But that rarely happens. So it's often if we're going back and seeing which one is having an impact, and then how do I optimize the future? How do I design the policy for tomorrow that's going to be effective? And the last example is sort of, we sort of, in this world, we think of sort of data as anything, right? It's data, everything is data. In that world, data comes in rows and columns. If it's not in a row or a column, it's not data. So in this case, it's like if the data happens to occur in voice form or speech form or text form or network form or video or audio, it's not data. So a lot of these projects, people sort of, I don't have data that can help me do this. And what they mean is, I don't have rows and columns that can help me do this. And so a lot of these projects are all around taking data that's not in rows and columns. I typically don't want to use the word unstructured because it's very structured. I am talking to you in a structured form. You are understanding me. So there's a lot of structure in what I'm saying, except it's not in a row and column form. So there's a lot of data, and so often a lot of these projects end up being creating rows and columns out of lots of different types of data. And actually, I'm going to skip through a couple of things because I have, how many minutes left? A couple of minutes left. So I'm going to skip through some of the more detailed things and talk about around detection. And basically spend a couple of minutes on when you start doing these things, sort of a bunch of challenges pop up, right? Which are not necessarily technical challenges. Privacy, security, which I'm not going to skip, but then interpretability. So if you're Google and you're trying to figure out what ad to show somebody, it doesn't need to be interpretable. It just needs to maximize the CPA, right? It just needs to make sure that the highest cost, you're making the most money you can off this ad. When you're a public health department, you're trying to figure out which kids to intervene with because you're going to miss out on other kids, you have to be pretty clear on why this model is predicting something. You have to be able to understand it because it could be wrong, it could be making a mistake. So for us, a lot of these public policy problems, interpretability is extremely important. And so the challenge is not to come up with sort of when you're building one of these predictive models, machine learning, is to explain the model overall, but also explain the predictions for each person. And those are two different things. And there's a lot of work that people are doing right now around this, but it becomes much, much more critical when you're dealing with these things that could affect people's lives. And the same is true of sort of the next thing, right, which is transparency. And transparency is interesting because a lot of these problems I talked about are adversarial, right, where the police officers, if they knew, so if you take the system that says if you've done 3 bad things in the past 180 days, raise a flag, one of the things we hear from police departments is that, well, an officer knows that and they've had 2 complaints against them and it's been 140 days, for the next 40 days, they're going to be careful. And they're going to be careful in 2 ways. They'll either not do anything for those 40 days, so nobody can complain about them, and that's bad, or they won't report things, or they'll try to make sure things don't get reported, and that's bad too. So we want to make sure that our system is transparent because it's making very important decisions about people's lives. You don't want to accuse somebody incorrectly of something, but you also don't want the system to be so open that people can game it. So there's this tension between transparency and what I'm calling sort of gameability. And we're trying to figure out how do you best do this so that you are interpretable and transparent, but still not too easy to game. The last piece here is about, again, because we're dealing with important problems about people's lives, we have a responsibility to be fair to people, and that becomes harder and harder as these things get complicated. Right? So, for example, if you start predicting, one of the things, if you're relying on historical data, and the data is biased because the decisions of who you're sending to jail, decisions who you're trying to prioritize, it happens a lot in lending practices. When banks have been making biased decisions for a long time, if you give that system to a machine, they're basically going to learn the same biases and propagate them and even exaggerate them. And that's not fair. So you can sort of look at some of that and audit those things and see, are you being fair to people? Are your predictions fair, even though your data may not be fair? But then the second thing becomes, who are you making mistakes on? Because none of these systems are going to be perfect. And you're going to make mistakes. Are you making mistakes unfairly about certain types of people because you don't have enough data on them? So we kind of need to make sure not just that we're making these predictions correctly and fairly, but that the ones we're getting wrong are not biased towards a certain group of people. And that's a really important and challenging problem here. A couple other things that, one of the things we want to also make sure is that people who are working on these problems have a skill set that is not just a skill set of, I know Python, I know scikit-learn, right? That is not enough. That's necessary, but it's not even close to sufficient. So what we're sort of found over the last several years working on these things is you want to have a collection of these skills. Yeah, you want to know programming because that's a basic life skill. But you also want to know how to formulate a problem. Because if you can't formulate that problem, that code isn't going to do anything useful to anyone. And you also want to make sure you can communicate the impact of that problem. Just to get that data and collaborate with a government agency, you can't just go in, walk with them and say, you have a really important problem that I can help you solve. You have to sort of communicate with them both in the beginning of that, during that, and then almost most importantly, at the end of that, so they actually are able to do something with what you've spent time doing. You want to be able to reason about ethical issues around it and legal issues. You want to know what HIPAA means because that's going to be the first word you hear from the other side. But HIPAA, it's like, yes, I know what it means. Here's how it works. Here's why this is okay, and here's how you protect against it and work with that system. You want to know how to design experiments because it's not going to be all data analysis. That's going to be historical data. But moving forward to validate these things, it's going to be a forward-looking actual trial and experiment. And you need to know, social science and machine learning. So there's a larger set of skills that you need than just a specific, knowing how machine learning works and how computer science works. And it's a much broader set of skills that you need to build. So basically, that's kind of what I had. I want to end with, if you want to know more about a lot of these things, the description of these projects are on our website. There's also a GitHub repo. Most of the code is open source. If it's not, because this program this summer just finished yesterday, and so what we end up doing is take a few days to clean up the repos of any passwords, anything else, and then release the rest of them on open source. So a couple of ones I talked about are not going to be there for the next week, but everything else is there. And then papers and descriptions are also over there. So, and if people want to get involved in this type of work, happy to talk more. Either find me after this or email me. Happy to talk to people about if you guys want to get involved in any of these things. But thank you. It's the wonderful Apple Twitter connection. Yeah.
Great talk. Thanks very much. One question that I had was about this interoperability issue. And so there's also this European initiative or something that teeth to it, where companies have to provide those interoperability models. And that can also explain why someone is not qualified for the model.
Right.
We're having very similar to the
Yeah.
And so there's a lot of interest in interoperability, and it seems like it's very subjective issue. And there's many models that claim to be interpretable. So how can you convince someone that the model is interpretable? How do we know something is interpretable?
Yeah. Yeah. So the question is, how do we know something is interpretable? How do you measure that? And I don't claim to know the answer here. Right? For me, it's very much the evaluation for me is a user study. Given two models that, let's say one of them is better in some other metric, how much more likely is your interpretability going to make this person use that model? And I think so. It's not. I don't think it's a technical definition. It's not. It can be described in n words or fewer, or the information content of that description is, in some number of bits. You can do some entropy. It's not about minimum description length. It's not any of the technical things. It's really, does a human who's making a decision, given this interpretation, is he or she more likely to take the right action? Which basically means, I think what we have to do is come up with different methods to interpret different models. I don't think it's, this model is more interpretable than that one. I think it's more, we have to think of interpretability as a separate function, that a model comes in and out comes from this interpretability function an explanation, not just for the whole model, but for each prediction. And now you're giving this human enough information, so you're giving them a way to explore the model, understand the predictions. It could be, I'm going to give you this person prediction is, this person is likely to be at risk because look at these 10 other people that you did something to in the last week, and 8 of them were just like this person, and they ended up doing this. So I don't think there's a technical objective answer here. I think it's really giving people tools to explore and understand these things, and then seeing which ways get them to do the right thing more often than not. But it's not going to be a, we're going to use logistic regression because everybody understands odds ratios. So, yep. Yeah, so that's why I was going to go through a little bit. So the question is, how accurate are these models? And the two metrics you care about are, you care about false positives. So how many people are you intervening on that didn't need that intervention? The second metric is false negatives. So kids who would have dropped out, who did drop out, but you didn't identify them. And typically what you see is, it's not exactly the same thing, but you end up sort of seeing this type of graph, right? And so on the left side, you've got how accurate are you? So if you identify, so for example, over here, we're saying is, hey, if I identify of my top 500 confident predictions, I am right about 40% of them. So 40% of them did drop out, let's say. And this red one is, of all the people who dropped out, how many did you capture in the top 500? So this is, if we just take this point, right? This point is 40 over here and about probably 30 over here. So this says in the top 500, 40% did drop out, and of all the kids who dropped out, 30% of them were in the top 500. So you want to, it's not, you don't want to pick one point on this graph. You actually want to plot the entire thing so you can then figure out, based on your intervention, how many resources do you have to intervene, and if you've only got interventions for 100 kids, you want to see which model do I pick? Because each model is going to give you different curves like that. And you want to sort of give that as a menu to the school district or the health department and say, okay, let's figure out what the right place to intervene is. So a lot of these results, if you look at some of the papers that we have, they're more sort of these types of graphs for different types of models, for different types of problems, for different types of school districts. So as you do that across, you get results that are very different. So you can't say, in general, for any problem, you get 80% and 60%. It's going to be very different based on how far out are you predicting. If you want to predict, the day before they graduate, whether they're going to graduate tomorrow or not, that's much easier than 5 years before. If you want to predict at a student level versus a class level or a school district level, that's much, individually is harder than group level, but sometimes you have group interventions where I'm going to put all these kids into an intervention. If you want to predict about an event that doesn't happen very often, so if you're a school district that only 6 kids drop out a year versus a school district where 10% of the kids drop out, that's the more data you have about a phenomenon, it's easier to predict. So there are different variables that make a behavior more or less easy to predict using these methods. Yeah.
Hi, thanks for the lecture. How do you take this and take it back to say the government of India or try to understand the data level of India and improve on say conditions or information? What is your advice to this?
Yeah, I mean, it's something we've tried to do a lot for trying to move to more where the need is higher in geographies and countries. The biggest challenge we have faced is that a lot of those organizations are not collecting data in a digital format, right? So a lot of data is on paper, if you're lucky, or in PDFs if you're less lucky. But it's not the PDFs, that you can easily parse. It's actually literally just pixels in a PDF. So the biggest challenge is really having that data. And so one of the things we've been doing, if you go on our website, is we call this data maturity framework. It's not a technical thing. It's basically different dimensions in which you need to collect data, how often you collect it, at what level of granularity, in what format, does it have unique identifiers, can it be linked? And that is mostly for people who are not here yet. They're not at the level where they can just run these things, but that's motivation for them. If you want to do individual level predictions of this type 3 years early, you need this type of data. And so the code is there. It's the challenge is the data isn't there. And then the awareness that this is a problem they can solve, that's not there. So the best way to take it to them is to kind of motivate them saying, you have this problem. In order to solve this problem, you need to collect this data. Once you have this data, here's an approach that helps you get from, because the middle part is easy. It's the getting them to care and understand that they can do this and showing them a path to get there. But happy to help with any, if you're interested, I'm happy to help with some of those things. So. Yeah, no, I think that's a. But if they have the data, then you can start small, where you can just give them a list of kids most at risk, and if they start testing that, if that works, then you can move slowly, as opposed to a big 5-year implementation. You can generate a list in Excel, right? You can do this. The output is a ranked list. You can give them an Excel spreadsheet, and they'll look at it and say, oh yeah, those kids are. So I think they need to kind of feel that that they can understand it, that it's not a massive, black box that's doing magical things, because it's not that complicated. So, sure. Yeah. So, yeah, whenever you want me to stop, last question? Okay. Yeah, so the question is, have we thought about using historical intervention data, whether it's a controlled intervention or whether it's just a natural, something happened. One of the challenges, so we've done that in some cases. One of the challenges is in most of these cases, it is common across pretty much all of these areas. Interventions never get recorded or rarely get recorded, especially at an individual level. And that's one of the things we're trying to do is, so that's what's one challenge. The second challenge is most of the studies that people do in intervention within natural or in a controlled environment, they are on it's basically a random sample of kids. And what we're trying to do is, yes, this intervention works on an average kid, but the coupling of prediction and intervention, that's what we really need to do, right? So you don't care if this intervention works on kids who are 98% likely to graduate. You care about how effective is this intervention on this kid. And that data is really, really, really hard to find because a lot of those interventions aren't there yet. So one of the things we're hoping to do is starting with this targeting, once we can identify the kids who are at risk, then we can get these schools to apply interventions on those kids. And then we can test and see which kids intervention A work on, which kids intervention A didn't work on. So that because the outcome is you've got 5 interventions, and I want to provide you a ranked list for every intervention of kids you want to put into those interventions. And we haven't been able to sort of get that intervention data. So if you know of anybody who's doing that at an individual level, happy to talk more about it. But thank you.